Hello, and welcome to 3.7. So the interesting thing about the derivative of a function is it can have the same meaning no matter what the function or the application you're dealing with. So it's always the limit of that difference quotient. So it describes the change in function values relative to the small changes in x values, no matter what the function represents. So the function can represent the height of an object, or the position of an object, or the quantity of something being produced. It doesn't matter. The derivative is going to have that same instantaneous rate of change interpretation. So we'd seen an application from physics before, last chapter when we talked about straight line motion. So this is an example of the position of an object being determined by a function, but the graph of the function isn't showing us the path that the object is at. So remember that the instantaneous rate of change of the position function is the velocity of the function. So if I take the derivative of my position function, I get my velocity function. For this problem I'm doing, it's actually number 3 in the exercises in section 3.7. It's asked for the velocity at time t equals 1. So looking at the graph of the derivative is this blue dashed graph. When t is 1, the derivative is 0. So that's telling me that the object is turning around. And if you look at the red square, let's wait, so now it's at 5 seconds, 5.5, 6 seconds. Let's have it go back. So now it's starting over from 0. So it's at 0.5 seconds. So see, at 1 second, it was turning around. So we already discussed this. This is the next part of the question. Asks when the function's at rest, and that's when it's changing directions, or when the velocity is 0. And we can see from the graph of the derivative function, that's when t is 1 and 3 and 5. So 1 second after it starts moving, it's turning around and going to the left. 3 seconds, it's turning around and going back to the right, and then at 5 seconds, it's turning around again and going to the left. So when is the object moving forward to the right? So the velocity not only tells us the speed of an object, but also the direction in which it's moving. So it's a directed value, it's a vector value. So when it's greater than 0, when the velocity is positive, that's telling me that this object is moving to the right. So we want to look at our velocity function and determine where it's greater than 0. So it's greater than 0 between 0 and 1 second, and between 3 and 5 seconds. So that's when the object is moving to the right. And just for point of clarification, I'm going to move back to my original slide for this problem. T is between 0 and 6. So I'm starting, the little red square starts here at t equals 0 and bounces back and forth in its path. It never goes to beyond 6. And remember that the horizontal axis is doing double duty. It doesn't go beyond 6 because this function doesn't apply beyond t equals 6. Now notice here that the horizontal axis is starting at -1 instead of 0. And that's because our little red object can move to the left of the origin because that axis is doing double duty. as the x-axis of our graphs and the axis that the object's moving on. So draw a diagram to represent the motion of the object. So as we can see, this guy bouncing around on this horizontal axis, it's backs up and moves forward again along the same path. So it's covering the same ground. So it's hard to trace the path on a single horizontal line because you're just going to be tracing over, when it's moving to the left, you're just going to be tracing over the line you drew when it was moving to the right, and you really can't figure out what's going on. So usually the path for a straight line motion like this is drawn in a snake-like diagram. You'll see that in the book. And arrows are put on each segment to show which direction the object is moving in. So at t equals 0, so at 0 seconds, notice it's moving to the right for 1 second, then it moves back at 1 second, to the left for 2 seconds, then back again for 2 seconds, and then it goes back to the origin at 6 seconds. So that's what we're showing here. When it started off at 0, it's moving to the right 1 foot. It turns around at t equals 1 and moves to the left 2 feet. It turns around at t equals 3 and moves to the right 2 feet. Then it turns around when t is 5 and moves to the left 1 foot. So these vertical segments are just showing where it turns around. They're not part of the path. So now they're asking to find the total distance traveled in the first 6 seconds. The length of the curve from 0 to 6. Now since the y values change sign, we can't just subtract y values. So if we need to look at the absolute value. So if we look at the absolute value of this piece as we could travel from here to here, that's f of 1 minus f of 0, and that's 1. If we travel from when t is 1 to t is 3, that's another segment. So f of 1 minus f of 3, again I'm taking the absolute value because I'm finding distances, and that's 2. And then likewise from here, this segment to this segment is of length 2. And I'm getting those lengths here because I'm subtracting the function value from f of 5 from f of 3. And then lastly, this segment, and I'm subtracting the function value at f of 6 from f of 5.